Welcome, everyone. So we've started to run the anti-cheating software and go through the results and find projects and homeworks that are similar to each other or similar to ones posted on Git. So this is the number of students who this morning have had scores of -20 or -30 entered as their new project or homework scores for these particular assignments. You should probably check glookup to see if you're one of the lucky recipients. If that includes those of you who know you didn't cheat, because there's always the possibility that somebody managed to somehow steal your code without your knowing it. So everyone please check glookup today. And if you find a negative entry in one of your homework or project scores, that means that you are accused of cheating. If you think that you did not cheat, you did not steal someone's code, you did not give somebody else your code, and that you're unfairly receiving a negative score, we've set up office hours with a TA that you can talk to and try to convince him that you're innocent. And so the first session will be today. Joel will have a session in 562B Soda Hall today from 3 o'clock to 6 o'clock. And so if you're falsely accused, please drop by and straighten things out with us. If you are not falsely accused, if you're correctly accused, if you did cheat and you know it, then we would actually prefer that you not drop by because there's a lot of people involved and it's going to take a while for Joel just to talk to the innocent ones. What else can I say? Oh, one thing I want to add is that this is the start. We have not yet gone through all of the possible Project 1s, Project 2s, and so forth that have been flagged by the anti-cheating software. We only lower your score if after the anti-cheating software flags your homework, a human looks through it and tries to decide what they think the probability is that real cheating went on. And so far, only if they think that they're pretty much convinced that it must have been cheating, do we go ahead and do this and enter a negative score. So if there's a negative score and you're surprised by that, then the most likely possibility is somebody stole your code. It's unlikely that it's a coincidence, but I suppose it could be. So please see Joel if you think that that's the case. There will be more people added to this list because we have more matches in the anti-cheating software that a human has not yet had time to go through and verify. And of course, we've got several other homeworks and another project that we're going to run this on. If you have not yet been caught for a certain event of cheating and you want to confess, then please send me an email, and the penalties are less for people who confess before we catch them. If you're already caught, then not so much. So today I'm going to introduce our last new data structure for the semester. It's called a Splay tree. It's not entirely new because a Splay tree is a binary search tree. It's exactly the same data structure in the sense of, if you look at the fields, it's exactly the same as a normal binary search tree. So we still use the binary search tree class and the binary search tree node class. The only thing that changes are the algorithms for inserting, finding, and removing items in a binary search tree. The reason why we're changing those algorithms is because the Splay tree is a balanced search tree. It's a binary search tree that keeps itself balanced, and the insert, remove, and find operations are designed to rebalance the Splay tree dynamically as you go every time you use it or perform an operation on it. So again, structurally, it's identical to a standard binary search tree. If you just look at one and you don't see the operation in action, you think it looks like a normal binary search tree. However, because the splay tree operations rebalance the tree as they run, all operations are going to run, well, not in log n time always, the way a 2, 3, 4 tree does, but definitely in log n time on average. Where n is the number of entries that are currently in the tree. Now, the average running time is not necessarily the same as the worst case run time. In fact, a splay tree can be just as bad as a regular binary search tree in that a single operation can take linear time. So these two things seem to contradict each other, but they really don't, because although it is possible that on very rare occasions a single splay tree operation will take theta n time, those rare expensive operations are balanced out by the fact that the vast majority of splay tree operations are much cheaper, so the average running time stays log n. Or to make a more precise statement, suppose you do suppose you do a sequence of k splay tree operations. And suppose that when you start with an empty splay tree. So you construct an empty splay tree, and then you do a sequence of k operations. And suppose that during that sequence of operations, the number of items is never greater than n. K, the number of operations, might be a lot bigger than n, but let's suppose that the tree size never grows bigger than n as you do inserts and removes and finds. Then all of those k operations together, that sequence takes k log n time in the worst case. So when I say that the average running time is log n, what I mean by that is that a sequence of k operations will take k log n time in the worst case, assuming you count all the way back to when you initially created the empty splay tree. And that k log n is not an average, that's an absolute upper bound. So, this seems like a weaker guarantee than what you get from 2, 3, 4 trees. A 2, 3, 4 tree guarantees that every operation takes log n time. Nevertheless, splay trees tend to be used more in practice, and there's several reasons for that. One is that the data structure is simpler, and because it's simpler and the operations are simpler, the big O, well, the constant hidden in the big O notation is often better. Another reason is that splay trees have kind of a magical property that they always restructure themselves so that items you have recently accessed are close to the root. So if you are accessing the same small group of items over and over again, the splay tree will be very fast. As a general rule, most applications don't look for all the different items in the tree with equal probability. They look for some items often and other items only rarely. If that's the case, then a splay tree will give you much faster access to the items that are accessed most frequently. And that's a big advantage sometimes. So again, if you have an application where the vast majority of the accesses are to a small proportion of the items, splay trees are a big win. They tend to actually do operations closer to constant time sometimes. So splay trees are actually the most used basic data structure invented in the last 30 years because for many applications they are the fastest kind of balanced search tree, faster than 2, 3, 4 trees for a lot of applications. Not all, but probably most. They're used in all kinds of software, some of which you've probably used, things like the GCC compiler, the GNU C++ library, the SED string editor, a lot of network routers on the internet, the most popular implementation of malloc for Unix kernels, the Linux loadable kernel modules all use splay trees, and they are also used in Windows NT in a bunch of different code. So the basic operation that we use a lot in a splay tree is called a rotation. And rotations are a way of restructuring a tree that lets us keep the tree balanced. So what does a rotation look like? Let's say you have a part of your tree where there's a node y in the tree. It may or may not be the root, but all I care about is the subtree rooted at y. Y has a child, which I'll call x, and we have some subtrees that are hanging off of x and y. We don't really care what's in those 3 subtrees, A, B, and C. We just care that they are still in the right place in the tree after we do the rotation. And so if you do a rotation to the right, what that does is it takes the x and it moves it up to the root, and now the y is the child of the x, instead of the x being the child of the y. And those 3 subtrees, A, B, and C, are still in there. They're still in their proper places, so that the tree still obeys the binary search tree invariant. And so you can see that everything is still in its proper place. Here, A is the set of all keys that are less than or equal to x, and over here, A is still the set of keys that are less than or equal to x. Likewise, C has all the keys that are greater than or equal to y, and still does after the transformation. And the most interesting part is the subtree B has actually moved. B was a child of x. Now B is a child of y, but B is still in the right place and still obeys the search tree invariant because B contains keys that are between x and y. So we're going to use this rotation to the right operation a lot, and we're also going to use the reverse operation of that, which is a rotate left. And a rotate left is not only the reverse operation from a rotate right, it's also the mirror image operation. If you hold it in front of a mirror, you've just flipped it around. When I say that splay trees are kept balanced with these operations, I mean approximately balanced. It's not perfectly balanced. So we're definitely not going to have a situation like a 2, 3, 4 tree where all of the leaves are at the same level of the tree. We're not even going to have a situation like a complete binary heap where all the leaves are at 2 levels of the tree. But over the long run, we're going to be able to achieve a partial balance that means that usually the height of the tree will be big O of log n. Not perfectly balanced, but usually the depth is log n. And when it's not, that's a very transitory situation that doesn't last long. So any questions about rotation operations? Yeah. It is not the exact same thing as a 2, 3, 4 tree rotation, but it's closely related. So now I'm going to go through the splay tree operations. Splay trees have the usual traditional operations of finding something in the splay tree, inserting something into the splay tree, removing a key from the splay tree. And if you already know your binary search tree operations, well, once you know one splay tree operation, you kind of know them all. So let's look at our traditional find operation. It's going to start exactly the same way it does in a binary search tree. So we start at the root, we walk down the tree the usual way we do in a binary search tree until we hit the key K. We find the node that has that key we're looking for. Or we hit a null pointer because the key we're looking for is not in the tree. Either way, so far it's exactly the same as a binary search tree, but then we're going to do one extra thing that we do not do in a normal binary search tree, which is we're going to take the key that we're going to take the last node that we just stopped at. We're going to take either the node where we found the key or the node where we didn't find the key, and we're going to splay that node up to the root by doing a sequence of these rotation operations. So I'm going to use a capital X to denote the node where the search ended. And so that node X either contains the key that we were looking for, or no node contains the key we're looking for, and this is about as close as we could get. And now we're going to take X and we are going to splay it up the tree. By doing a sequence of these rotation operations. And the goal is that X should become the root of the tree. So, if we found the key we were looking for, that key is going to be the root of the tree now. If we didn't find the key we were looking for, some other key that's close to that key is going to go up and become the root of the tree. But either way, this helps to rebalance the tree if it is unbalanced. If we're searching for a node that's too deep, well, this will bring it up so it's not deep anymore. And if we search for it again, we'll find it really fast next time. So now the question is, how do we use rotations to splay X to the root of the tree? Well, we're going to have to look at 3 different cases for how we use those rotations. And so I will go through those cases one by one. So it's a little bit tricky to get the tree to become rebalanced or better balanced as a result of doing rotations. And you can almost do the obvious thing, which is just keep moving the key one level up the tree, one rotation at a time, until you're at the root. But that doesn't quite work. That doesn't quite rebalance the tree properly. So we need a slightly more complicated set of rules. The first case we're going to look at is if X is the right child of a left child. Or the mirror image of that. So what that means is I have a situation where I've got a grandparent G, a parent P, and the node X that I am trying to splay up to the root of the tree. And X is the right child of its parent, which is a left child of the grandparent. And these three keys also have little subtrees hanging off of them all over the place. So we're going to need to account for those. So in this case, we're going to do basically the obvious thing. We're going to do a rotation that brings X one level up, and then another rotation that brings it one more level up. So the first rotation is X rotates to the left through its parent. And so now X is going to be the child of its former grandparent. And then the next step is that we do one more rotation. Now it's a rotation to the right that brings X up to the root of this subtree. Now, at this point, if this is the whole tree, X is the root of the tree now, but this might be happening way, way down the tree. G might be a child of some other node, and now X is the child of that node. Question? Mm-hmm. So the question is it just the most recently accessed node that is quick to access? Well, if you access one node A and then a different node B and then a different node C, when you access B and C, it brings them up to the root, but A doesn't drop very far. The splay operations are only going to make A go maybe one or two levels down. So A and B are still close to the root of the tree. So everything you've accessed recently is not too far from the root. Let's see. So, of course, if you have the mirror image of this case to start with, if X were instead the left child of a right child, then you would do all of this in mirror image as well. So you would do a rotation to the right and then a rotation to the left. And this particular case, the original authors call this the zigzag case, because you zig to the left and then you zag to the right. Oops, wrong button. All right. The second case is going to be essentially the opposite of case one. Now we're going to look at what you do if X is a left child of a left child. Or the mirror image of that. This case is the more interesting case because in this case we do something that's a little bit counterintuitive. We don't do the obvious thing that we just did of rotating x up and rotating x up again. We do something slightly different. Let me draw this case. There's the grandparent and the parent of x. And once again, they probably have some subtrees hanging off of them that we should keep track of. Now, the thing we're going to do different here is we're not going to rotate x through its parent first. Instead, we're going to rotate the parent through the grandparent first. And, this is the most important part to memorize for the final exams, this is the non-intuitive case. You need to start by rotating through the grandparent before you rotate through the parent when you have a left child of a left child or a right child of a right child. And so having done that, that brings the parent up to the root. Now that that's done, now we can do a standard rotation of x through its parent. So once again, we rotate right, and that brings x up to the root now. And in this example, both rotations are going in the same direction, and the authors of the original paper call this the zigzag case. So you got a zigzag operation and a zigzag operation. And again, if you have the mirror image of this case, if x is a right child of a right child, then the operations you do are the mirror image of what you see here. So you rotate left through the grandparent, and then you rotate left through the parent. So now that we have these two cases, what the algorithm is going to be is we're going to find x in the Splay tree by the standard binary search tree find operation, and then we're going to splay it up towards the root 2 levels at a time. So you either follow the zigzag or the zigzag rule, and that brings x up 2 levels. And then you do it again. You bring it up another 2 levels, another 2 levels, and so on. So you're going to repeat these 2 rules over and over again. Until x reaches the root or the child of the root. If x reaches the root, you're done. If x reaches the child of the root, well, you can't apply either the zigzag or the zigzag case anymore because you don't have a grandparent anymore. So that's where case 3 comes in. If x is just a child of the root, then you just do one more simple rotation that brings x up to the root. So if x is a left child, we'll rotate right, and that brings x up to become the root of the Splay tree. And this case is just called zig. And that's the find algorithm for Splay trees. So now let me demonstrate this algorithm. Here is an example of a binary search tree. And again, this should just look like a normal binary search tree until you actually do a find operation. There's nothing different between a Splay tree and any other binary search tree until you do an operation. So what we're going to do here is we're going to do a find 7. And so we start at the root, up at the 11, and we walk down the tree the usual way, and eventually that brings us to the 7. And now we need to splay the 7 up to the root before we return it. So how do we do that? Well, first of all, notice that 7 is a right child of a right child. So this is the zig-zig case. And that means we start by rotating through the grandparent and then through the parent. So after we do that, the tree will look like this. So the 7 has moved 2 levels up the tree. You can see its former parent, the 5, and its former grandparent, the 3, have been rotated down. And now once again, we check out the status of 7. Is it a left child of a left child or a right child of a right child? Well, no, it's a left child of a right child. So that means this time we're going to apply the zigzag rule. Remember, we just applied the zig-zig rule, but the next one's going to be a zigzag. And what that means is that we'll rotate 7 through its parent first, and then through its grandparent. And after we do that, now the 7 is a child of the root. So again, the 7 has moved 2 more levels up the tree. It's a child of the root now, so now we just use the simple zig rule to rotate it 1 more time so that the 7 becomes the root. Any questions about that? Yeah. Is it possible for a tree to be more imbalanced? It is. I'll probably show you an example later if time permits. But the funny thing is that there are cases where you insert a new item, the tree becomes a little bit more imbalanced than it was before, but that doesn't actually mean that the operations are particularly slow. So the average operations are sometimes even faster when that happens. But eventually, once you start doing searches that are down the deep part of the tree, they will break up that imbalance very quickly, so things will go fast. It's hard to explain exactly why that happens, but if I have time to show some examples, that'll maybe clarify it. Question?
So can we compare the height of the right subtree and left subtree to separate imbalances?
There are algorithms that actually do look at the height of the left subtree and the right subtree and try to improve the balance that way. This is not one of them. So I think there's some algorithms like that in the Goodrich and Thomasia textbook if you're curious to learn them. But this one sort of magically doesn't look at the heights and gets a great answer anyway, or great results anyway. Mm-hmm. So the splays themselves, each rotation just takes constant time. So the thing that decides how fast this algorithm is going to be is how deep you have to search in the tree. And that's it. Whatever the depth of the node you're looking for is, it's going to be big O of D time to do that operation. So the splaying does make the constant a little bit bigger for find operations, but actually, because it tends to bring frequently accessed items up the tree, it's actually going to make up for the extra cost of doing this restructuring. Yeah? Applications for what? So I gave a list of them earlier, which I can say again. Examples are Unix malloc. You have a large heap where you want to allocate objects. How do you allocate objects? You need to keep track of all the different bits of empty space in your memory and how big those pieces of memory are, so that you can search the right piece of memory when you need it. And a splay tree is one way to do that. Any search tree will do it, but they use splay trees because they just tend to be the fastest search trees in practice. Mm-hmm. One reason why we balance the tree with the find method is we often search for exactly the same key many times. If you look at real-world applications that use search trees, you'll find it's very common that certain keys get searched over and over and over again. And so if you have a really deep tree, well, let me draw this example a little more cleanly. Let's consider this tree here. Now, splay trees are not always perfectly balanced, and in fact, it is possible to get a splay tree that looks like this if you, say, insert all the items in order. But having an imbalanced splay tree like this isn't usually a problem, because if you do search for one of the deep nodes in this tree, the tree will rebalance itself within a few searches. So although that one find operation will be very expensive, it's going to get rebalanced pretty quickly, and you can't do a lot of find operations that are unbalanced. So let's suppose you do a find one. Then, yeah, you're going to have to spend a lot of time walking down the tree to get to the one the first time you do it. But after you do a find one, first of all, the one now moves up to the top of the tree. So if you do another find one, the next find one is going to be really, really fast. But secondly, you can also see that along the search path where you searched, the items that were on that search path have roughly had their depths cut in half. And you can even quantify that. A node, if it's initially at depth D, and it's on the access path, so you do a find operation that walks through that particular node, then that node that was at depth D that you walked through when you did your find, that's going to get moved up to a final depth that is less than or equal to 3 plus D over 2. So if D is really big, it's going to get cut approximately in half. So not only will the next find one be much, much faster than this find one? But a find for anything on that access path that's deep will be approximately twice as fast now as it was before. Question here. Mm-hmm. Right. So in this example, you can't say that find one always takes log n time, but you can use amortized analysis, which I'll talk about next, by the way, to prove that the average running time for find one is log n. Question here? So if you have a list of numbers and you want to make a balanced tree by finding the median and dividing it into two sets and doing that recursively, then yes, that's very doable. You can use the median finding algorithm, the selection algorithm that I taught last week, to find the median recursively, repeatedly. Or you can just sort the array. And then once you've sorted an array, it's very easy to make a perfectly balanced tree out of that. What's hard is if you're constantly inserting and deleting items, then you have a list that's changing just a little bit with every insertion and deletion. And if you want to keep that balanced every time you make a change, and you want those changes to be fast, that's more challenging. So algorithms that do that generally don't create perfectly balanced binary trees. So having done that, oh, by the way, this is also an example of why we need the zig-zig rule. The zig-zig rule is what caused the depth of the tree to sort of get cut in half. So we wound up taking something that was linear and straight like this and turning it into something that's kind of staggered in these two element stacks. It's the zig-zag rule is what did that and helps us cut down the depth of the tree in cases like that. So now that we know how to do a find operation, all the other operations are going to be straightforward. The formula is always going to be do the same thing that you do for a binary search tree, but then splay something to the root. So if you want to do the min or max operations, then first you just find the entry with the minimum or the maximum key. You remember how to do that. If you want the item with the minimum key, start at the root, go left, 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 until you can't go left anymore. And once you get there, you've got that entry with the minimum or the maximum key, then you splay it to the root. Exactly the same way you splay a key to the root in the find operation. What if you want to insert a new item? You can probably guess where this is going. You insert the new item into the splay tree exactly the same way you insert it into a binary search tree, and then you splay the new item to the root. That's it. The remove operation, as usual, is going to be slightly more complicated. All right, so what we're going to do is we are going to start by doing the standard remove operation for binary search trees. All right, so we start off exactly the same way we do with a normal binary search tree. So you recall we search and we try to find the item. If it's there, we have several rules for removing it, depending on whether it has 0 children or 1 child or 2 children. And if we don't find it, then we're just going to search down the tree like we do with a find operation and wind up at some node where there's a null child pointer where we expect the key to be. If we succeed in finding and removing a key, then we're going to let X, capital X, be the node that is removed from the tree. Now you'll recall that if the key we are removing has 0 children or 1 child, then X contains that key. But if the key we're removing has 2 children, then we have to go search further down deeper in the tree to find another key that we can move up to replace the key with 2 children. It's that lower down key, that's the node that actually gets removed, so X would be that node. And then we splay X's parent to the root. We can't splay X because we've removed it, but we can splay its parent. Another way to think of this is that we splay the deepest node that we visited and didn't actually remove from the tree. We can't splay the node we did remove from the tree, so we splay the deepest one that we didn't remove, which is the parent of the one we did remove. So for instance, if I, say, have a tree like this, and let's suppose I want to do remove 2. You will recall that in a binary search tree, when you want to remove something that has 2 children, you can't remove the root node. What you can do is you can find its next larger key, the minimum key in its right subtree, and move that 4 up to replace the 2. So in that case, the node X that I've been talking about is that 4, because that's the deepest node we visit, doing a standard binary search tree remove operation. So the 4 gets moved up to replace the 2. The node that contains the 4 is deleted. And now it is the 5, the parent of X, that gets splayed. So we're going to splay that 5 up to the root, and that leaves us a splay tree that looks like this. Any questions about that? All right, one final thing to note is sometimes the key you want to remove is not in the tree. You still have to splay something. This is a general rule of splay trees. If you do an operation, you have to splay something. The something that you have to splay is the deepest node that you visited that's still in the tree. So if you try to remove a key, and it turns out that key is not in the tree, well, you still might have had to search really deep to find out that that key is not in the tree, so you'd better splay the tree and rebalance it so that if you have to do that search again, it won't be as deep next time. Any final questions about splay trees? Mm-hmm. So every splay tree operation is exactly the same as the corresponding binary search tree operation for the first half. Like, they all start out exactly the same as a standard binary search tree operation until you're done the standard binary search tree operation. But they're all different because you always have to splay something at the end. Yeah.